Good morning. My presentation is about development of a three-dimensional numerical model of sediment transport and morphological evolution on sandy beach. In this presentation, firstly, I will give an introduction about background of our investigation, and secondly, general framework of three-dimensional numerical model. Thirdly, coupled nearshore wave current model. Fourth, three-dimensional phase average model of nearshore sediment transport. Fifthly, comparisons between model simulation results and the measurements at laboratory. And finally, conclusions. We have all known that coastal erosion is a growing problem in many countries due to natural and human effects. It is said that over 70% of sandy coasts are in a state of erosion, so it is very, very important to accurately predict the coastal evolution so that we can evaluate hazard due to erosion or take coastal protection measures. In recent years, numerical models have become very popular to describe sediment transport and coastal morphological evolution. We have coastline models and coast profile models, coastal area models. Coastal area models include depth average two-dimensional models and three-dimensional models. And the three-dimensional model is more and more widely used with the development of computational capability. For three-dimensional models, we think that several aspects are to be improved. The first one is the three-dimensional reduced stress. There is no bottom slope effects in previous three-dimensional models. The second one is the asymmetric sediment transport during wave period. And the third one is the real-time coupling of wave, current, and sediment transport in unstructured grid system. So the objectives of our presentation are to employ a new formulation of three-dimensional radius stress to describe nearshore wave current more accurately. The second one is to include asymmetric sediment transport due to waves to describe cross-shore sediment transport more reasonably. And the third one is to realize real-time coupling of wave, current, and sediment simulation in unstructured grids to describe the nearshore processes. And here is the framework of a three-dimensional numerical model. We use SWAN model and FECOM hydrodynamic model. They are coupled through MCT and they provide parameters for multi-class sediment transport model and morphological model. First, let's see the coupled wave current model. The axis of waves are expressed in these reduced stress terms and surface roller terms here. As for reduced stress, we used the new three-dimensional reduced stress we derived in 2017. In our new expression, the bottom slope effects are reflected in these terms. This reflects the bottom slope effects. And the parameters in these expressions are as follows here: FSS, FCS, FSC, FCC, and N1, M2, and N2. Then, the modified FECOM model and SWAN model are coupled through model coupling toolkit, that is MCT here. After the coupling wave current model is developed, we set up the sediment model. We use the multi-class advection diffusion equation to compute suspended sediment transport. Here is the advection diffusion equation. Bedload are divided into two cases. One is the bedload transport due to combined waves and current. Another one is the sediment transport for skewed asymmetric waves. And finally, the morphological evolution model is here. To verify our model, we collected different experimental data. The first example is long-shore current due to obliquely incident waves on a planar beach. This is carried out by Hamilton and Eberson. We can see the simulated results agree well with the mirrored one. Here is the wave height, mean water level, and depth averaged long-shore current velocity, and this is the vertical profile of a long-shore current. The second example is the undertone due to normal incident waves on a planar beach. The measurement was made by Qinhe. We also see good agreement of wave height, mean water level, and cross-current profile. Please note the black solid line is the simulated profile of our model. The third example is about rip current for barrel B morphology with rip channels. The experiment was carried by Hans and Svensson. We have good agreement for flow field and velocity profiles. Here again, the black solid line is our simulated result of our model. From the fourth example, we compare the morphological evolution. Here is the trend migration due to combined waves and current. This experiment was conducted by Varroy. We can see simulated flow velocity, sediment concentration, and bed profile agree with the measured values well. The fifth example is about sidebar migration. For offshore sidebar migration, we have good agreement between simulated and measured values. Here is the wave height, the mean water level, velocity profile, and the sediment concentration profile. And finally, the beach profile changes after 18 hours of wave action. For onshore sidebar migration, wave height, mean water level, velocity are good enough. The sediment concentration and the beach profile, here is the sediment concentration we can see, and the beach profile change are satisfactory, but not good enough as in offshore migration. The last example is about morphological change around the Qinhe breakwater, carried out by Grievance and Wang. Here is the simulated wave height and cross-shore velocity, long-shore velocity, bathymetry control. These values all agree with the measured data. Now let's come to the conclusions. We developed a new three-dimensional numerical model of nearshore sediment transport and the morphological evolution of sandy coast in unstructured grids. Firstly, a compound view current model system, including SWAN and FCOM, was developed using a new three-dimensional radius stress formulation incorporating the bottom slope effects. Then, a sediment transport morphological model for multi-class non-cohesive sediment was implemented. The suspended load transport is computed by solving a three-dimensional advection diffusion equation for multiple sediment classes, and the bedload transport was calculated by summing of the transport by current plus sinusoidal waves and skew asymmetric waves. The model system was validated through measurement of the long-haul current, undertongue, rip current, transmigration, sidebar migrations, and bed change around the T-head growing at laboratory. We have seen that the onshore sidebar migration is not so good as offshore sidebar migration. That means the onshore sediment transport is not simulated good enough, so the improvement of onshore sediment transport simulation is needed. And we also found that the coast side transport is not simulated satisfactorily, so the improvement of coast side transport is also needed. And we verified our model through laboratory experiments. So the validation of long-term simulation of morphological evolution in field is also needed. Thank you for your attention.